G'day and welcome to my next video for Math Methods Unit 2, Introduction to Probability, Conditional Probability. What I have up there is an example of a type of situation that you might be asked to turn into a Venn diagram. 12 students play golf, 20 students play soccer, and 8 students play both. So, what we need to do is we need to turn that into a Venn diagram. Now, a lot of people would just assume that the numbers that they need to write in are, so this is golf, this is soccer, and then in the middle is both. But that's not how it works. Because what you need to remember is the overlap. What is going on here? Right? Knowing what we know about this situation, we need to create some new numbers to go in just G and not S, and just S and not G. Because otherwise, these 8 kids are being counted multiple times, which is no good to anyone. So I'm actually going to get rid of these numbers here. But what I do know is that the total number of kids inside the black circle needs to be 20. And since 8 of them are in this overlap, therefore there must be 12 in that side of the bracket. So inside the black circle is 20. But because 8 of them are inside the purple circle as well, therefore the number of students not inside the purple circle, but still inside the black circle is going to be 20 minus 8, which is 12. And then following on with the same logic, there are supposed to be 12 kids in total in the purple box, but there are 8 over here, therefore there are only 4 here. And that gives me a total number of students of 24. So there are 24 students in the class. Now, if I was to talk about all the different probabilities that came out of this, so what is the probability of picking a kid who plays golf? Well, there are 12 kids who play golf. I've already said it. 12 students who play golf. There are 20 kids who play soccer. How many kids are there in total in the class? There are 24. Every kid is accounted for. No kid plays neither. We assume. But this is where the idea of conditional probability comes in. What is the probability of picking a kid who plays golf, but I know plays soccer? What is the probability of picking a kid who plays golf, given that I know he plays soccer? All right. So what is the probability of picking a kid who plays golf, given that I know he plays soccer? And that's represented like this. The probability of G vertical bar S. The probability that a kid plays golf, given that he plays soccer. Now, how many kids in this situation do I actually care about? All right. All right. The probability that he plays golf, given that we know he plays soccer. So there are 20 kids. There are 20 kids who play soccer. There are 20 kids who play soccer. And of that, how many of those students play golf? 8. Therefore, the probability is 8 out of 20, which is 2 out of 5. So that's 40%. So if I'm only so what these given that's mean is that I am restricting the total number of students I care about. Like, for example, what is the probability I pick a face card in a deck of cards given that I've picked spades? Well, if I pick spades, if I'm only caring about spades, then there are only 3 face cards that I care about. That means the probability in that case would be 3 out of 13, not 3 out of 52. So if we were to go the other way, what is the probability that I pick a kid who plays soccer given that I know he plays golf? So the probability that he plays soccer given that I know he plays golf. How many kids play golf? Well, 4 plus 8 is 12. How many kids inside play soccer? Well, that's 8. Therefore, the probability is 2 over 3. What this serves to illustrate is that the probability of A given B is not the same as the probability of event B happening given A. So when you're doing these sort of calculations, you need to make sure that you've got them the right way around. So in the case of my example there, on the condition that we know he plays soccer, what is the probability that he plays golf? So on the condition that he plays soccer, what is the probability that he plays golf? Now, where this comes in handy is, again, there are some more formulas that we can use. And we can actually use that to help shortcut some of this work. The probability of A given B is equal to the probability of A and B divided by the probability of B, assuming B isn't 0. All right, assuming B isn't 0. So that if the probability of B 0, because the moment it's a probability of B being 0, then you're suddenly you are undefined errors, etc. All right, and then this formula here can also be rearranged. So if you were doing a Carnot map before and you're only given a particular piece of information, you've got a formula there that you can use to help untangle other bits of information. There is one more formula that I know people like to use, which is the probability of A happening is equal to the probability of A given B times the probability of B plus the probability of A given not B times by the probability of not B. And again, so that's called, so we've got here, we have the conditional probability. But this here is called the law of total. The law of total probability. And as long as you have these formulas, you can use that to fill out and complete probability tables and do all sorts of working out regarding particular things happening or not happening, especially if you are picking from a restricted pool.